Hello and welcome to Electromagnetics 1. Dr. Trample here. This is lecture number 14. Today we'll be talking about magnetic scalar and vector potentials. Well, as a way into this, let's talk a little bit first about what a vector potential is, or what a potential is in the most general sense. In the most general sense, a potential is simply a quantity upon which you operate with an operator to yield a field. Okay. So today we're going to be talking about two different such potentials: the magnetic scalar potential, which is a scalar, and magnetic vector potential. They're both useful, but in different situations. So let's first look here at the magnetic scalar potential just a little bit. Remember, we've been studying magnetostatics, okay? So we're not allowing there to be any non-zero time derivatives, essentially. So all the derivatives with respect to time fall out in Maxwell's equations. In that situation, the magnetostatic Amperes law, if you remember, is the curl of the magnetic field is equal to capital J, which is the electric current density, okay, in amps per meter squared. Well, let's say that we're in a region here, in a source-free region, where there is no external electric current density. In other words, capital J is equal to 0. In that case, and only in that case, the magnetostatic Amperes law becomes the curl of the magnetic field is equal to 0. If you'll remember, we have a particular theorem that we can use in this situation, which says that if the curl of a vector field, any vector field now, is equal to 0, then by the irrotational theorem, we can write that same vector field, in this case the magnetic field, as the gradient of some scalar potential. By convention, we also tack on a negative sign out here, but because the magnetic field is, we say, irrotational, or its curl is equal to 0, then we can write the magnetic field in this way, as the gradient of a scalar potential. Here, capital V sub m is the magnetic scalar potential. Now, why would we be interested in doing this? Well, it is sometimes easier to work with a single scalar quantity rather than a vector quantity. Remember, this vector has 3 components in the most general sense, versus this single scalar. So sometimes it's easier to work with the magnetic scalar potential. This only works, again, in source-free regions when you have the magnetostatic situation. Okay, now we have another Maxwell's equation here that we're going to use. Recall that Gauss's law for magnetic fields may be written in this way: the divergence of the magnetic flux density, capital B, is equal to 0. Okay, so what we're going to do is we're going to further assume the constitutive relationship for the magnetic flux density and the magnetic field is given by capital B is equal to mu h. So we're just going to assume a linear isotropic constitutive relationship here between the magnetic field and the magnetic flux density B. Then what we're going to do is we're going to substitute this expression for the magnetic field into Gauss's law for magnetic fields, like so. So here we make that substitution. We say B is mu h, and we're going to further say AH, capital H, is minus the gradient of the magnetic scalar potential. We're going to put those two facts together, substitute this thing into here, and you end up with this equation right here. The minus the permeability times the divergence of the gradient of the scalar potential is equal to 0. And there's an identity here that you can use, which is the gradient of the divergence is the Laplacian. Dividing through by the scalars, we arrive here, which is the Laplace equation. So, interestingly, at least in the situation where you have a linear isotropic material, the magnetic scalar potential also satisfies a Laplace equation, just like the electric scalar potential, voltage, did in the electrostatic case. So if we understand how to solve the Laplace equation in the electrostatic case, sometimes we can solve the Laplace equation in the magnetostatic case, and then after we find out what the magnetic scalar potential V sub m is, then we can go back and operate here with this gradient on the potential to get the magnetic field H when we're all done. So that's the magnetic scalar potential. All right. As I mentioned before, there is also a magnetic vector potential that can be useful. All right. Again, it's a potential, which means we're going to operate on it with some operator in order to get a field. We may again take advantage of Gauss's law for magnetic fields. I've just simply again stated Gauss's law for magnetic fields here, which says that the divergence of the magnetic flux density B is equal to 0. Okay. If you recall, there's another theorem that we looked at earlier in the course called the Solenoidal Theorem. If the divergence of a vector field is equal to 0, we say that vector field is solenoidal. Okay. So in this case, since the divergence of the magnetic flux density B is equal to 0, then by the solenoidal theorem, we can write B as the curl of a vector potential capital A, where capital A is the magnetic vector potential in this case. Okay. So because of the Gauss's law for magnetic fields here, we can write B as the curl of the magnetic vector potential A. Again, this can be calculationally useful to us. Further recall the magnetostatic Amperes law again. Now here, this is the more general magnetostatic Amperes law, where we have not assumed a source-free region. So there can be an external electric current density capital J in the region. That's okay. So we're going to say, okay, in the magnetostatic case, the curl of the magnetic field is here equal to the electric current density capital J. All right. Now what we're going to do is we're going to again assume a linear isotropic relationship between B and H. And so we're on the left-hand side here, we're going to say mu H is the curl of capital A. Divide both sides by mu, and we arrive at this equation, which is H is 1 over the permeability times the curl of the magnetic vector potential. Okay. Okay, our next move then is to substitute this expression right here for H into Ampere's law. So I'm going to substitute H right into here. So it's going to get the following will happen. When we substitute 9 into 8, we get 1 over mu curl of A is equal to capital J. Multiplying both sides through, we have curl of A is equal to mu J. I'm trying to derive a wave equation here, or I should say a particular equation. So just bear with me. The next thing that we need to do after we write the curl of A is equal to mu capital J is we need to operate on this left-hand side here with the following vector identity. This vector identity says that the curl of A is the gradient of the divergence of A minus the Laplacian of A. Okay, and this is a vector Laplacian in this case. Okay, I'm simply going to operate on the left-hand side of this equation with this identity right here. And I'm going to further say that we're going to be using something called Coulomb's gauge right here, which is we are going to apparently arbitrarily at this point set the divergence of the magnetic vector potential equal to 0. Okay, so if we set the divergence of A equal to 0, this term goes to 0, And we can simply say that the curl of A is minus the Laplacian of A, like this. And then finally, this equation with this simplification becomes the Laplacian of A is minus mu times the electric current density J in amps per meter squared. Okay. This is called the vector Poisson equation right here. It's the vector Poisson equation. A couple of things to be aware of and to be careful of when you're working with this. Remember, this operator here, this vector Laplacian, is just that. It's vector valued in the sense that it operates on a vector quantity, capital A. So when you are attempting to use this, make sure to look up the definition for the vector Laplacian, not the scalar Laplacian, which is different, but the vector Laplacian in whatever coordinate system you happen to be working in, either rectangular, cylindrical, or spherical. Okay, so it's, again, this vector Laplacian is different in all three coordinate systems. Okay, so you have to see what coordinate system am I in, and then look up the most general expression for the vector Laplacian of A, okay, in order to solve this equation. It may be shown that the following three expressions satisfy this vector Poisson equation right here. So if you have a line current, like so, this is the expression for the magnetic vector potential that will satisfy the vector Poisson equation right here. Again, you're integrating over the source, whatever that happens to be, wherever your current is, and integrating right here, dl prime, and dividing by, in the kernel, 1 over r. Remember, that is the magnitude of a vector that connects a point on the source to your field point, to the place where you want to know the field. That's the expression for a line current. If you have a surface current, you do a two-dimensional integration, again, over the surface here, ds prime, and capital K is your surface current density. Similarly, if you have a volume current, capital J, then you use a volume integration. So you're going to have a triple integral. Okay. These are these integrals. You can show that if you substitute this expression right here into this equation, so if you operate on this quantity right here with the vector Laplacian, it will give you the right-hand side. Similarly for here, and maybe we can see this more clearly for the volume current, if you substitute this expression right here into this equation, so if you operate on this whole expression with the vector Laplacian, it will give you on the right-hand side minus mu j. So that's what it means to satisfy that equation. Okay. Well, what else would it be interesting to know about? We've been using the Biot-Savart law, but we have not, in a sense, justified it. We've not proven it. Okay, so I'm going to show you a little bit here about where the Biot-Savart law comes from, so that you have some mathematical grounding for that. Okay. Well, the first thing we're going to do in order to derive the Biot-Savart law is we're going to take this expression here for the magnetic vector potential due to a line current, and we're going to substitute it into this equation right here. And we're going to say that the magnetic flux density is going to be equal to the curl of that particular magnetic vector potential. Okay, so that's what I'm doing first off right there. So we're going to say that B is the curl of A. We're going to divide both sides through by the permeability and arrive right here at equation 17, which says that the magnetic field is the curl of this expression right here. Okay. Now, In order to further simplify this expression, we're going to need another vector identity right here, which is equation 18. So what this vector identity says is the curl of the product between a scalar field f and a vector field capital F. The curl of that product is equal to little f times the curl of capital F plus the gradient of little f crossed with the vector capital F. All right, and in order to apply this identity right here to this equation, number 17, we're going to set f, we're going to say our scalar field is 1 over capital R right here. And we're going to say that our vector field f is simply this dl prime vector right there. So 1 over capital R, that's little f, and dl prime, that's going to be capital F. Okay, so I'm just going to substitute for those two things into this vector identity, and that's what you see here in equation number 19. All right, so if you set f equal to 1 over r, capital F equal to dl prime, you get this. The curl of dl prime over capital R is 1 over capital R times the curl of dl prime plus the gradient of 1 over r crossed with dl prime. That's just each of the terms here in this vector identity. Okay. Well, now we're going to make an observation that will help to simplify this, which is the following. This gradient here, this gradient, operates only on unprimed coordinates. Okay, it's only operating on the unprimed coordinates. Notice that dl prime is a function only of primed coordinates. So dl prime is in a sense a constant with respect to this operator. So the derivative of a constant is equal to 0. So the curl with respect to unprimed coordinates of dl prime is equal to 0. So this whole term is going to fall out. The next thing we need to observe, and I'm going to just simply quote this here and not derive it, but notice that also you can do some simplification on this term right here, the curl of the gradient of 1 over capital R. We can do some simplifications of that. And it turns out that you can show this rigorously, that the curl of 1 over the magnitude of the displacement vector there, capital R, is equal to minus r hat over capital R squared. Okay. So I'm going to substitute in this expression right here for the gradient of 1 over r. And when you make that substitution and plug it back into this expression right here, voila, what pops out is in fact the Biot-Savart law. So one of the takeaways there is just simply that the Biot-Savart law is a consequence of the way that we can use the magnetic vector potential, essentially. That's where it comes from. It comes from the magnetic vector potential and the fact that the magnetic vector potential satisfies Maxwell's equations in the magnetostatic case. Okay. The next thing that I would like to do is to show you an example of how we can apply some of these things. So let's apply this to a particular example. And I'm going to scale things a little bit here. Well, let's consider this problem. We would like to know what the magnetic vector potential due to a rotating charged disk is. So here's the setup. Just imagine that out here in space, you have a charged flat disk of radius little a. Okay, so it's sitting here with its axis aligned with the z-axis. And this charged disk carries a surface charge density equal to rho sub s. So Just imagine that you've scattered, you'd evenly distributed charges across the surface of this entire disk here. So just evenly distributed across the disk, there are some charges that have accumulated on it. And then you come and you just start spinning the disk at a constant angular velocity omega. So the disk is then rotating. What happens when you do that, when you think about it, right? Charges moving at a constant velocity are magnetostatic currents, really, are DC currents. So by turning the disk, you are creating some DC currents. Because the velocity isn't changing, it's a magnetostatics problem. So we can use all the machinery that we developed for magnetostatics to solve this guy. Well, what are the steps? What do we need to do in order to solve this problem? I'm just going to zoom in here just a little bit here. Okay, what are the steps that we need to go through in order to solve this? Well, the first thing we need is we need an expression for the surface current that's rotating around on this on the surface of this disk. Okay. The best way to approach this is to start with this particular equation, and what this equation here is saying, it says U is equal to omega cross R. So what this is saying is that the velocity of a point on the surface of this disk is given by this equation, omega cross the vector pointing from the origin to that particular point, R. Okay. Let's say that our disk is rotating at an angular velocity omega naught. That means that our omega vector can be written omega naught in the z hat direction. It just points straight up. We need to use cylindrical coordinates for this particular problem. So we're going to write this r vector that goes in this equation as rho pointing in the rho hat direction. It just points from, like if we're interested in this point right here, there'd be a little vector that points from the origin right to there. That is the rho hat vector. To get an expression then for the velocity of that point as it rotates around, we just perform this really simple little cross product here. It's just omega naught z hat crossed into rho hat. Z cross rho gets us phi hat. So U in this case is omega naught rho in the phi hat direction, essentially. Which makes sense. We know that no matter where we are, the velocity of a point rotating on this thing should be pointing in the phi hat direction. Okay, now once you have an expression for the velocity u, you can develop an expression for the surface current density, capital K, right here, by just simply multiplying u by the surface charge density, rho sub s. So rho sub s u is by definition K. So to get an expression for capital K, we just multiply this guy by rho sub s. Ta-da! We now have an expression for our surface current density. Okay? Now, once we have an expression for our surface current density K, then we are going to use the integral expression here for the magnetic vector potential. So we're going to say, okay, the magnetic vector potential due to that rotating, that particular surface current density K is given, as we saw in the previous few pages, by this expression right here. This is a surface current, so you need to integrate over the surface, the entire surface of this disk. Okay, and it's mu naught k prime ds prime divided by 4 pi times capital R, where again capital R is the magnitude of the distance between the observation point, where you want to know the field, and a point on the surface that's contributing to the magnetic vector potential at that point. Now the game is, the next part is to simply go through here very carefully and systematically and figure out, okay, what's K prime, what's ds prime, and what is capital R. Okay, we are in cylindrical coordinates. We want to integrate over a surface that is in the xy plane, essentially, in cylindrical coordinates. So our ds prime is given by rho prime, d rho prime, d phi prime, just like that. Okay, that's the little chunk of area that sits on the surface of this disk. All right, well, let's go ahead and substitute in for ds prime here and for k prime here. So k prime is rho s omega naught rho prime phi hat prime. That's where those things come from, substituting in here. And then ds prime is rho prime, d rho prime, d phi prime. That's where these terms come from. So in the end, what you have is, in order to figure out what the magnetic vector potential A is due to this rotating disk, you have to compute this integral somehow. Integral from 0 to 2 pi, that takes you all the way around once, and from rho prime going from 0 up to its radius A. That integrates over the entire surface. Well, it turns out that in general terms, for the most general case, actually computing this integral is difficult. So if you want to know what the magnetic vector potential is at some point, say off the axis and very close to the disk, you would have to calculate this integral numerically, which you certainly could do. So this is as written. This is exact. This is an exact expression for the magnetic vector potential due to that rotating disk, valid anywhere at any point in space. This expression will work right here. Let's say that we want to know, we would like to know what the magnetic vector potential looks like when we're very far away from the disk. That's called the far field. So we're a long way away from the disk now. Let's see if there are some simplifications that we could make in order to make it so that we could simplify this integral and get a closed form expression out of this. Okay. Well, what we're going to do is we're going to play two games. The first thing we're going to say is we're going to say that we're in the far field. Okay. What does that mean exactly? It means that our observation, the magnitude here of our observation point vector is much, much larger than our source point vector, essentially. So the unprimed coordinates are much bigger. The magnitude of this vector here is much bigger than the magnitude of that one, essentially. We're a long way away. That's the first game we're going to play. The second thing we're going to do is we're going to say, let's see if we can get an expression for this when we have a particular value for phi. We're going to set phi equal to 0. So remember, this is the observation coordinates now. So what we're going to say is we're going to be observing this magnetic vector potential at some point along the x-axis. That corresponds to when phi is equal to 0. Okay? And then we're going to argue and we're going to say, okay, if we can find the field there along the x-axis, it's got to be the same anywhere else there as we rotate around 360 degrees because the geometry itself is symmetric. It has azimuthal symmetry. So we're going to argue that if we know the field along the x-axis, we actually know the field at any point at the same value of z, at the same height, rotated around 360 degrees. Okay, that's the argument. Let's see if we can pull that off. Okay, well, the first thing to observe here is that when you set phi equal to 0, so you're on the x-axis, you're observing in the x-axis, you can make this particular approximation right here. You can say that the magnitude of the displacement vector, capital R, is approximately equal to the magnitude of the observation vector, little r, minus rho prime times sine theta cosine of phi prime. Well, how in the world do you come up with that approximation? let's look at this picture right here. This essentially tells the tale here. If you're going to say that the magnitude of R, say, is really big relative to the magnitude of rho prime, okay? This is the picture that you can write. So here we are. We're at a particular theta. Okay, remember that's the angle between the z-axis and the r vector in spherical coordinates. Okay, so we're at a particular angle theta here. All right, and in this particular case, it turns out that the difference between this length, okay, and this length, r prime, the difference between those two is approximately equal to this total length right here minus this little short distance right there. As long as r is very, very far away, as long as you're in the far field here, okay? So that difference, that whole thing minus that, is this length right here. So if you drop a perpendicular down here from rho prime and subtract this projection off, you end up with this approximation, which gives you an approximation to the difference between this vector, the difference between the magnitude of that vector and this vector right there, essentially. It's an approximation. It's not perfect, but it's good enough for our purposes. Okay. In order to make further progress, we need yet another approximation. And so we're going to say, okay, if the magnitude of little r is again much, much bigger than rho prime, which it is, then what we can do is we can actually apply a Taylor series to this expression right here. Okay. Well, what's a Taylor series? We'll come back to that expression. Remember what a Taylor series is. It says that locally, about a point x naught, you can approximate a function f of x as approximately that function evaluated at x naught plus the first derivative of the function evaluated at x naught times x minus x naught, delta x. Okay, so this is an approximation to this function. Here's what we're going to do. We're going to say, okay, we're going to have, in our case, we're going to let x be equal to r minus rho prime sine theta cosine phi prime, like that. We're going to say our x naught is going to be equal to r, and the function that we want to approximate is 1 over x. Okay, so if we apply that Taylor series expansion to this function here, this is 1 over x, we get 1 over x naught, or 1 over r, minus the derivative of this, which is minus 1 over r squared, times x minus x naught, which is this term right here. And after we simplifying it, we end up with this guy being approximately equal to this right here. Okay. All right. One more observation, then we'll put it all together and see where we end up. The other complication in dealing with this integral right here is that this phi hat prime vector varies as you move around the disk in phi. This is actually varying as you are calculating the integral. That makes it tricky. So one of the things that we do is we rewrite phi hat prime as cosine of phi prime y hat minus sine of phi prime x hat. This is just an identity that comes from cylindrical coordinates, essentially. Okay, so we're going to put all this stuff back into our integral now. We're going to approximate this 1 over r as 1 over this first. 1 over that expression, right, is this expression right here. And then we're going to further approximate this expression with this expression. Okay, so we're going to substitute in where 1 over r is, we're going to put this thing. 1 over capital R used to be, we're going to put this expression right into here. That's where this term comes from. That's replacing 1 over capital R. Then the next thing that we're going to do is we're going to substitute the phi hat prime for this expression. We're going to substitute in that expression right there for phi hat prime. Okay? That's where that term comes from. Okay? Now let's see if there's anything that we can do with this expression. Now let's see if we can do something with this expression. Well, oh yeah, there we go. That was falling off this edge of the screen. So yeah, so you've got your cosine phi prime right there. Okay, let's look at a couple of things that are going to help us out here. This integral right here as a function of phi prime, if you integrate, think about you're integrating this sine of phi prime from 0 to 2 pi. That's an odd function. So it's going to actually integrate to 0 as you integrate around from 0 to 2 pi. So this whole term is going to fall out. And we're only going to have to deal with the y hat term. So the x hat component is going to go to 0 because when you integrate the odd function, it's going to integrate to 0. And we just have to then deal with this cosine of phi prime y hat term. Okay. Now, if you look at this here, when you integrate again, when you integrate cosine of phi prime times this from 0 to 2 pi, this guy also, even though it's not odd, I should say, there's as much positive area as negative area. So that's actually going to integrate to 0, just like sine phi prime did. So this term, the 1 over r term, that's not going to contribute. The only thing left is going to be the cosine of phi prime times cosine of phi prime term out here with the 1 over r squared in the denominator. And so that's, if you make all of those simplifications, you get down here just to this particular integral right here that just has a y hat component. The integration over rho prime right here is trivial. You're just integrating rho prime to the third. That's rho prime to the fourth over 4. Evaluated from 0 to a. That's where the a to the fourth comes from. And then you just simply are integrating cosine squared phi from 0 to 2 pi. That term doesn't fall out, and when you carry out both of those integrations over rho prime and over phi prime, voila, you end up with this expression right here. So in the far field, on the x-axis right here, this is the expression that you get for the magnetic vector potential due to a rotating disk of charge. We can make, as I mentioned before, we can make the argument that if that's what it looks like on the x-axis, it's going to look the same thing at any point of constant rho and constant z in a circle. And so we can actually replace this y hat with phi hat in this case. And this is the most general expression for the magnetic vector potential for the rotating charge disk in the far field. Okay. Well, thank you very much for your attention, and I'll see you in the next lecture.